Hi everybody, welcome back. So today we're going to do multiple equation models. And multiple equation models are going to open up a whole new vista of methodological models and methodological solutions and methodological problems that we can tackle and different ways of thinking about the world. They'll deal with identification, which turns out to be a problem even in single equation models, but I saved it until here because it comes up much more frequently in multiple equation models. We'll deal with the infrastructure necessary to solve problems in missing data. And there'll also be a multiple equation model that is associated with that. They're called seemingly unrelated regression models. We'll talk about reciprocal causation or endogeneity, which is a real problem in social science research. It's a fundamental problem in observational research that we will address in any event. And finally, we'll talk about multinomial choice models. We talked about logit and probit models for dichotomous dependent variables. We talked about ordered data where there's 1, 2, 3, 4, 5, and we don't know the distances between the 1, 2, 3, 4, and 5, but they were all on the same scale. Well, what if you have a choice of 5 candidates where they're not really on a particular scale? Those are multinomial choice models. Okay, so these are the subjects or the subheadings within multinomial models, and that's what we're going to do today. So let's get started. So here's our outline: identification, seemingly unrelated regression models, reciprocal causation, and multinomial choice models. Identification first. So first of all, a definition of identification, you may have heard of it, but here's the idea. A qualitative definition, a simple intuitive definition is what we can learn when about the parameters of the statistical model when n goes to infinity. I mean, it should be the case that if n goes to infinity, we can basically learn alpha and beta in the generalized version of the statistical model pretty much exactly, right? We should, but in identified models, you can't. So this is a pretty important thing to know. Mathematically, the definition of identification is that each parameter value produces a unique likelihood value. Graphically, we can think about this as a likelihood function where there is no unique maximum. Maybe it's flat, maybe there's a plateau at the top. If there's no unique maximum, then it's not identified. There are partially identified models where the likelihood is informative about only a range of parameter values. I mean, if there's a plateau and it comes down on the sides, then you sort of know the maximum is somewhere in there, or there is no maximum really, but that range is what we should focus on. But sometimes it's not identified at all, in which case there's basically no information about that parameter value at all. That would be a non-identified model. The non-identified models are likelihoods with non-unique maxima. These models, if you really understand them, really don't make any sense at all. But if they don't make any sense, why would we use them? Well, it turns out it's hard to know sometimes whether they don't make any sense. And so we will be able to determine, once we understand identification, whether they're dumb models to begin with. So Unifying Political Methodology, Chapter 8 will focus on identification. You can have a look at it. All right, so first are flat likelihoods. So let me invert this. Instead of asking, is this model identified? If it's not, then it's dumb. Let me just start with a model that we can transparently see as dumb, and then we'll see that it's not identified, and we'll understand what not identified means, and then we'll be able to take that to more complicated cases. So here's a model, a dumb model. So y follows a Poisson distribution. Okay, so far, no problem. But then we have a truly dumb systematic component where lambda, the expected number of events, is equal to 1 plus 0, not x, but 0 times beta. Now that's dumb because obviously beta, no matter what beta is, it's not going to affect the likelihood, right? So you're not going to be able to estimate beta from the data, right? I think it's transparent here that you're not going to learn anything from this. But that doesn't stop us from writing it down. And it also doesn't stop people from writing down non-identified models of all sorts. Anyway, so what do we know about beta solely from a likelihood perspective? So now let's imagine that we don't fully understand or know or that this is a dumb model. Perhaps it's not transparent to us that it's a dumb model, as it will be in more complicated cases. So let's just follow likelihood and see what likelihood tells us. Fortunately, likelihood will tell us that this is not identified. So here's the likelihood function, product of our I equal 1 to n of the likelihood of the probability distribution, which is Poisson. The log of the likelihood function is the sum of the logs. I've substituted in the systematic component here. That's what these two pieces are. The whole thing is equal to, the whole thing simplifies, right? Because 0 times beta is actually 0, so that drops out. Then the whole thing is equal to the sum of -1, which is equal to minus n. So the likelihood function is equal to minus n. Now, remember my notation that it turns red and gets embarrassed if it's not a function of the parameter and drops out. So that's actually the case here. I'm going to leave it in because then there's nothing left to put in. Okay, so let's graph it. Let's have a look. On the horizontal axis is beta. And then we can ask the question, well, what does the data say about beta from the likelihood theory of inferences perspective? So what we would normally do is we would say, well, what is the log likelihood value at different values of beta? And the answer here is they were all exactly the same. An identified likelihood has a unique maximum. That is one point that beta is at the maximum. A likelihood with a plateau is not identified, has no unique MLE, but could be informative. In this case, there's no information at all, right? There's no value of beta along the entire real number line that conveys any more information that has no higher likelihood than any other value, okay? So this is a dumb model, but you can see it's dumb. It's very clear. Even if it's not clear at the beginning, you can tell from likelihood. So likelihood reveals the dumbness, okay? All right, let's look for a case in which you may have run into, and we could think of it as a non-unique reparameterization. So this is the problem of collinearity. We all know that you can't have perfectly collinear explanatory variables in a regression equation. So what happens from the likelihood theory of inference if you try to do that? So here's a model. Y is normal, just like in a regression model. Mean mu, variance sigma squared. And then I'm going to have a linear function. So mu of I is equal to a linear function of x1 beta 1, x2 beta 2, x3 beta 3. Okay, no problem, except x2 and x3 I'm going to say are the same. So obviously they're perfectly collinear because they're exactly the same variable. All right, well that means we can simplify the systematic component. So it's equal to x1 beta 1 just as before, but then I can pick either x2 or x3 to represent both of them. So I pick x2 and I write it this way. Okay, so I collect these terms. Okay. So now let's ask the question from the perspective of likelihood. What's the unique MLE, maximum likelihood estimate, of beta 2 and beta 3? Okay. Well, different parameter values lead to the same values of mu, and thus the same likelihood values. And so here's an example. So if we substitute in 5, right, 5 here for beta 2 and 3 here for beta 3, turns out we're going to get the same value of the likelihood, the same value of mu, and therefore the same value of the log likelihood when we substitute it into the systematic component. So beta 2 being 3 and so whatever beta 2 and beta 3 are, you can swap them and you're going to get the same likelihood. So that's an example of a non-unique reparameterization. And a likelihood surface, the height of the likelihood, that's going to be the same for both of those codings. It can also be for 7 plus 1, anything that equals 8, basically. Okay. The likelihood of, another way of saying it is that the likelihood for beta 2, 3 and beta 3, 5 is the same as the likelihood for beta 2, 5, beta 3, 3. Okay, so that's non-unique reparameterization. If it wasn't clear to you to begin with about collinearity, you could derive it from likelihood. In fact, if we had taught this class right from the beginning, before you had a prior class in statistics and before you had any experience with the idea or any knowledge of the idea of collinearity, we could just derive it. In fact, this page totally derives it. You don't really have to know things ahead of time about collinearity. You can just do this and you could say, oh, I shouldn't do that. And it makes sense that I shouldn't do that. That's the whole point of likelihood here, the likelihood analysis here. It really makes sense that you shouldn't do that. Okay, that's identification. Obviously, there's a lot more to identification than that, but that's all you need to know right now. Because when we run into non-identified models, which happens more frequently in multi equation models, we'll know what it is. Okay. There is, of course, a big literature on that, as pretty much everything else that we work on in this course. Okay, so now let me talk about one specific multiple equation model, which is going to be seemingly, I'm going to work up to it, it's going to be seemingly unrelated regression models. Okay, so for starters, here's a generic multiple equation model. We'll start with a joint stochastic component. I've put in the matrix dimensions underneath each of the symbols so we can follow along. So the key thing here is the stochastic component is unusual based upon anything we've seen before. Y of I is not a scalar. It now has capital N things. So capital N is not the number of observations. Little n is the number of observations. But for this one observation, for the first observation, let's say, there's going to be capital N things in that vector. So this is going to be a multivariate normal distribution, which if we drew observations from it, would give this vector. So that's the key thing. Theta I is an n by 1 vector. Alpha is an n by n matrix. If this were normal, the mean theta I would be the mean, and alpha would be the sigma variance covariance matrix. And this whole thing exists for I equal 1 to n. Okay, so that's the stochastic component, the joint stochastic component. Now, before I write down the systematic components with plural, think of the stochastic component as, well, there's a whole bunch of outcomes, but what we could have done is run equation by equation models, one for each of the elements there, and then instead of having an n by 1 vector here, we'd have one of those elements. So what we're doing is we're taking separate models for each of the scalar outcomes and putting them together. So we're going to have to ask ourselves, when is it worth doing that? When should we put the whole thing together versus keep them separate? Okay, so let me go on and continue to define this multiple equation model. So now we have the systematic components for the stochastic component. The stochastic component has capital N of these things. Remember, this is the part with the stochastic component. This with the systematic component, this is not. So let's write down the systematic components, one for each element of theta. So here's one for the first element of theta. Here's one for the second element of theta, all the way down to the capital Nth element of theta. So I have this written generically. So G is the functional form. If you want, you could have separate functional forms for each one of these, separate vectors of explanatory variables, or perhaps overlapping, in some cases anyway, and different effect parameters. So you see the complexity, it gets more complex, but you might have run these analyses as separate analyses. So we need to ask, when should we run them together? So we'll get there. Okay, we need an independence assumption for every model so we can figure out how to use the different observations together in one model. And we're going to do something directly analogous to what we've had before, which is yi is independent or orthogonal to yj for all I not equaling j. Now, just remember that y of I and y of j each have n elements, okay? So this is not an assumption about the relationships among the elements of y sub I or among the elements of y sub j. It's the independence across people. So you can think of this as we collected 5 variables for each person, and the 5 variables are, capital N is 5, but we have 1,000 people. Okay, and the independence assumption here is independence across people, not across within the 5 things. Because within a person, if you ask 5 questions, they're going to be related in some way. You wouldn't want to make an independence assumption about that. Okay. So when, you keep asking this question, let's actually answer it. When is a multiple equation model better than n separate equation by equation models? And the answer is when the elements of y given x are stochastically dependent or parametrically dependent, when they share some correlation or non-independence in the stochastic component, or they share parameters in the systematic component. Let me show you each of these. So the full probability with, I'm going to write down the full probability model from this big model with capital N equal 2. So just a 2 equation model. Simplest case, again, following the same rule about understanding about methods. What you do is use the simplest possible case. So multiple equation models are not so simple, but a 2 equation model is is simpler than a 20 equation model. So we'll start with 2. So here's our equation. We have 2 outcome variables y and 2 parameters, and I'm setting aside the other parameters. We're going to assume stochastic independence. What does that mean? That means we can factor the stochastic distribution into 2 parts. So that's our stochastic component. Now, because of this assumption of stochastic independence, we can factor it into 2 parts. Now, what enables us to factor it into 2 parts? Well, y1 and y2 are going to be independent given theta 1 and theta 2. Okay, I've assumed alpha away like we do in the stylized normal model. Okay, so now we have these 2 components here. Okay, now let's write down the log likelihood. What's the log likelihood? Well, it's the log of the sum is the sum of the logs, right? We have the 2 pieces here. Now let's just make one more assumption. The second assumption, we'll assume parametric independence, and all that means is theta 1 and theta 2 don't share any parameters. So, I mean, you could say that this is a vector. I mean, this presumably would be a vector, and this would be a vector, just like in a normal likelihood model for one equation. But we might want to say that beta 3, the third element of this, is equal to the third element of this, right? If we assume that away, we assume there's no parametric independence in addition to the stochastic independence, then running a multiple equation model is equivalent to maximizing separate equation by equation models. And you can actually see that here. Like, let's look at this. So we're maximizing this whole thing, all right? So with respect to theta 1 and theta 2, or if you have a systematic component, you'd substitute those in and do it with respect to beta 1 and beta 2. But if these parameters are not shared, remember we factored these because of stochastic independence, so now we have these two components. If the parameters, if theta 1 and theta 2 don't have any shared values, then what do we get for that? We get the fact that when we're trying to maximize with respect to theta 1, this whole component turns red and goes away. This whole component is a constant, right? It's not a function of theta 1, and so it doesn't matter. Similarly, when we're trying to estimate, we try to find the maximum likelihood estimate of theta 2, we can drop this first component. So that shows you directly that equation by equation maximization of the parameters separately, in this case where you have stochastic and parametric independence, will give exactly the same answer. Okay. All right, so now let's take that and build a specific model. So the specific model we're going to build is called the seemingly unrelated regression model. I think it probably should have been called the seemingly related regression model because the individual regressions, which in fact we're going to run, are sort of seemingly related when you were running them as separate regressions, and we don't really know how to put them together until we have the seemingly unrelated regression model. So we'll call it SURM. It is sometimes called the seemingly unrelated regression model estimator, or a regression estimator, which is SURE. So SURE, it's called SURM. Anyway, so here's the model. This model will come back to us when we do missing data. All right, so Y follows a normal distribution. Mean y is again multivariate. Is multivariate. This is going to be a multivariate normal distribution, mean vector mu, variance covariance matrix sigma. The systematic components for mu are each linear regressions. So there's going to be one for each j equal 1 to big N, and each one of those is a linear regression. On the bottom of each one, I just have the dimensions of the matrices to help remind us that they're matrices and to know what the dimensions are. If you ever get confused by matrix algebra, write down the dimensions underneath and make sure they're conformable, right? That this kj is equal to this kj. In any event, I do that. And the third component of the SURM model is that yi is independent of yj for all I not equaling j. And again, I'm making the same assumption as I was before about independence across people, not within people across measures. All right, so what's the likelihood function? Likelihood function is the product, because of independence, the third assumption, of all the stochastic components from the first assumption. We then substitute in the formula for the stochastic component, and that's what we get. We then, we can then go ahead, of course, and substitute in the systematic component for each of the mu's, and that's how you form the likelihood function. Okay, let's keep going. So if y given x are stochastically independent and the betas from the different regressions are parametrically independent, then SURM produces equation by equation least squares, just like in the general case, for the same reason that I showed you. So for SURM, so you think about what SURM is. SURM is you have a set of regressions. So suppose you have the democratic proportion of seats in the state legislature in each state in the United States, and the democratic proportion of seats in the state Senate in each state in the United States, and you have 50 observations, except Nebraska only has one house, and so maybe there's 49 observations. So you have 49 observations. What do you do now? You could run 2 separate regressions predicting those on the basis of economic conditions and approval of the parties and things like that. But you have basically 2 parallel regressions going over the same observations. If you had stochastic independence, no reason you do with this case, because if the voters of a state are more democratic, they might vote more democratic for both houses of the legislature. And the betas are parametrically independent. And I don't know whether that's true, of course, because maybe the incumbency advantage is the same in the state house and the state senate, or maybe not. I mean, you have to think about that. But if they are, then there's no reason to put it together and bother yourself with SURM. You could just run separate regressions. But if they're not, and I think they're probably not, then it's actually better, more statistically efficient. You'll get smaller standard errors if you run one big SURM rather than equation by equation least squares. You get out regression coefficients that are estimating the same thing as the individual regressions. You just get smaller standard errors. That's useful sometimes, right, if you don't have that many observations. Okay. In any probability density function, let's just remind ourselves that stochastic independence, probability of A and B, is equal to the probability of A times the probability of B, implies mean independence, which implies uncorrelatedness. Okay, so what does that mean? So if we have y this way and x this way, or if we have y1 this way and y2 this way, and I want, actually let me do it this way. So if we have y this way and x this way, and we want to say they're uncorrelated, then you just fit a linear regression and it's flat. So that's no linear relationship. Mean independence is the following. For every individual value of x, or in bins or something like that, we take the mean of y. So remember, y is vertically, x is horizontally. We take the mean of all the y's that have this value of x, and we put it here. We take the mean of all the value of y's and we put a dot here. We take the mean of all take the mean of the y's for this value of x, the mean of the y's for this value of x, the mean of the y's for this value of x, and we plot just the means. If all those means fall in a straight line, that's mean independence. Mean independence is a stronger assumption than uncorrelatedness. Because if the means go like this, then the best linear regression is a flat line. They're uncorrelated, but they're not mean independent. Stochastic independence, what's that? That's a more full relationship among the variables. In fact, it's, any relation, if there's any relationship among the variables, then they're not stochastically independent. Stochastically independent says that for the same regression, we have y vertically and x horizontally, same regression. For every value of x, there's a distribution of y. There's a distribution of y, there's a distribution of y, there's a distribution of y. And those distributions under stochastic independence are the same, okay? So that's stochastic independence. You can, if you have uncorrelatedness, you may still have mean dependence. If you have mean dependence, you may still have stochastic. If you have mean independence, you may still have stochastic dependence. For example, if there's mean independence, so the means are all flat, you'll also have uncorrelatedness. But suppose the variances are increasing. If the variances are increasing, then there's no stochastic independence. Okay, so that's perhaps a review, perhaps not. That's true in any probability density function. If, however, you went ahead and you said, I'm narrowing down from any probability density function to just the multivariate normal, well, in the multivariate normal, the only relationship among the variables is linear. That's the only way you can have a relationship, because just by assumption. So that means if you have linearity, if you have no linearity, if you have uncorrelatedness, you get mean independence and you get stochastic independence for free. Now, it's not really for free because it's by assumption. You made the assumption when you chose multivariate normal. But nevertheless, you only have to test for uncorrelatedness if you've already made the assumption of multivariate normality. Okay. One other fact. This is an interesting fact. It works out this way. In addition to the fact that SURM is equal to equation by equation least squares with stochastic and parametric independence, there's another case, and that is the case of identical x's. So if the x's that you put in to predict y, to predict the Democratic proportion of the state legislature and state senate, if those x's are exactly the same, regardless of parametric or stochastic independence, then you get exactly the same answer. Equation by equation least squares is the same as SURM. So in order for SURM to give better answers than, or different answers and almost surely better answers than equation by equation least squares, you have to have non-identical explanatory variables and you have to have not stochastic independence and not parametric independence. Okay, so the identification, so now think about some model, not one that I'm showing you now, but one that you're reading about, some big complicated nonlinear model. And you're trying to figure out what this model is, okay? And somebody says, I had to run this big complicated model because I have lots of outcome variables. You should think to yourself, are they getting anything from this model over and above what they would if they ran separate and simpler equation by equation models? The bigger the model, the more likelihood of model dependence, right? So we're going to have to worry about that more. So if they have to run some big model, you should be skeptical about it. Make sure that they really need to do that. Why do they need to do that, right? So let's take a special case of a big nonlinear, non-normal model. Well, in that nonlinear, non-normal model, these results of uncorrelatedness implying stochastic independence and identical x's implying that the multiple equation model is equal to the equation by equation models, those don't hold, but they hold approximately, okay? They hold in the best linear normal approximation to whatever this person is doing, okay? So you keep that in your mind. Why should you keep in your mind the wrong model? You should, because it's a simplification of their more complicated model, and the rule that I keep giving you is to understand a complicated methodological situation or model or problem, go to the simplest possible case. This may very well be simpler than the simplest possible case, but as an approximation, it's often pretty good, and it'll at least give you intuition. If they have identical x's and it's a nonlinear model, then you have to ask, where are they getting identification from of the multiple equation model separate from and better than the equation by equation models? Where are they getting it from? They're getting it from the assumptions about nonlinearity and the assumptions from about non-normality. Are those plausible? You would then get to zero in on those assumptions, ask the person questions about them, see whether it's worth your time and everyone else's time, and figure out whether the resulting model dependence from having a big modeling structure is worth it. Okay. In multiple equation models, programming is more complicated. Y is not a scalar, it's a vector, and so the whole data matrix of Y is not a vector, it's a matrix. There are lots of computational tricks in the context of every one of these models to make things go faster, but you should just remember that that's true. And if you want to run one of these models, see if there's some software available. If not, then you should just remember, yeah, Gary told me that there are some tricks, and that way it's possible to look them up. So the next topic that multiple equation models enable us to tackle is reciprocal causation. That just comes up all the time in observational work, and so we really need a way of at least thinking about it. There's a whole range of statistical models to try to deal with it. Today, I'm going to give you one very simple approach, not one that you should necessarily use, but one that you should absolutely use for intuition. All the other methods depend upon this basic intuition, and I want you to figure out whether and when and under what circumstances you might be able to use a statistical model to figure out reciprocal causation. Okay, so reciprocal causation, I mean when you think X causes Y, but the world doesn't comply, and actually it's Y is causing X. So how do you deal with this? Let's think about it from a multiple equation model perspective. So first of all, we're going to have a stochastic component. Simple multiple equation stochastic component, in this case for two variables. We have y1 and y2. We're going to assume that they're bivariate normally distributed, so there's two means and two variances and a covariance. That's the stochastic component. There's two systematic components, and I'm going to give you a specific example just to get a good feel for it. One is to try to explain the vote, and another one is to try to explain partisan identification. I once gave a talk at the Centers for Disease Control, and I talked to them, and I got to spend the whole day there, and then at the end of the day, I gave a talk, and they said, "So what did you learn from your day here?" And I said, "Well, the first thing I learned is that PID is not partisan identification." So you can look that up if you like. In any event, it was very funny for the Centers for Disease Control, and maybe not for our audience. But in any event, every discipline has its own jargon. This is our jargon, partisan identification. So vote, here we're going to have vote. This is the expected value of the vote. Let's say the vote for the Democrats is going to be a function of three variables, and party ID is going to be a function of three variables. Let me now define what those three variables are. And the parameters. Our quantity of interest is beta 3 and gamma 3. Okay, but what's the variable? I skipped over it. So you see, right, because it just looks like three variables. But the third variable here, mu2, is actually the left-hand side here. And then the third variable here is actually the left-hand side here. So what are we saying before I define the other variables? What we're saying is that the expected vote, mu1, causes or has some effect on partisan identification. And the expected partisan identification has an effect on vote. Now, what that means, we'll have to figure out. Whether we can estimate it, we'll absolutely have to figure out. But it is something that is a coherent sentence, right? It could easily be the case that those expected values actually belong here. We don't know how to estimate it, but let's go and figure out what the likelihood theory of inference tells us about those. Okay, so let's take it as our quantities of interest, that what we want to know is beta 3 and gamma 3. Pretty weird because we don't observe either mu2 or mu1, but nevertheless, it turns out we can actually estimate them under some assumptions, but that's going to be the key. Okay, so let's make this a little more realistic. First of all, we're going to have some variables in both equations. Let's imagine those are demographics, right? Demographic, age, sex, gender, etc. And then we're going to have some variables that are in the first equation, but not the second equation. So what would predict the vote, but not more stable partisan identifications? Well, perhaps characteristics of the candidates in this election, right? There might also be variables that affect partisan identification, but not the vote in this election, like your parents' partisan identification. I know that you may think that your parents' partisan preferences are not going to influence you at all, and that may be true at first, but it's a very reliable prediction of political science that eventually, or more and more over time, they're actually pretty predictive. Perhaps because you grow up in similar circumstances, perhaps because you find their wisdom reasonable. But whatever it is, there's some variables in both equations, some variables in one equation, some variables in the other equation, and not the other. Now, when we have a variable in one equation but not the other, that's not just like throwing a variable in. We have x2 in this equation. It is implicitly in this equation, in the second equation also, with a coefficient that is restricted to 0. Right? And similarly, x3 is in the second equation, but it's also in the first equation with its coefficient implicitly restricted to 0. Those 0 restrictions are big assumptions. Okay. So what's the likelihood? Here's the likelihood. We take the product over the n observations of the multivariate normal distribution. We plug in the exact form of the multivariate normal distribution. That's what we get. But this is there's one more step here, because when we have mu I in both places here, and we substitute in these guys, it doesn't work, because if you substitute in mu1, if you remember, mu I is mu1 and mu2. But if we substitute mu1 in wherever we see mu1, we get mu2. And if we substitute mu2 in wherever we see mu2, we get mu1. So it doesn't reduce the complexity, right? The whole idea of reparameterization is to reduce the number of parameters that we have to estimate. And it doesn't do it here. So what are we going to do? Well, and so the real question is, how do you substitute in the systematic component to take that information into account when you form the likelihood function in a multiple equation model like this? So the goal of reparameterization, as I said, is to reduce parameter dimensionality. Standard models reparameterized in a basic way. You substitute mu in for x beta, and mu, by the way, has n components, and x beta only has k, right? Because there's only just the number of betas. There's time series models, which I haven't shown you, but they reparameterize recursively. You take the past and you put it in, and it keeps going. There's multiple equation models now, which give us multiple equation reparameterization. Okay, so let's do that. Okay, now I'll show you what multiple equation reparameterization is. It's to use, the idea is you use both equations at the same time to solve this problem. So I wrote down the first equation and the second equation, highlighted in red and green mu2 and mu1 respectively, just so we can keep track of them. Now let me solve the problem with respect to the first equation, then I'll do the second equation. So first of all, I'm going to take mu2 in the first equation right here, and I'm going to substitute in what we know from the second equation. So we just take the right-hand side here and substitute it in for here, and that's what we get. Well, not much, it doesn't solve the problem because the right-hand side here still has mu1. However, when we started here, there was mu1 and mu2. Now there's only one of these annoying variables. So what are we going to do now? So now we multiply out, we just distribute out those parentheses, and we still have that mu1, so what are we going to do? Well, we have mu1 on both sides of the equation. We can take that last term and subtract it from the left-hand side and combine the mu1s. What happens then? That's what happens. You see that? So now we have mu1 on the left-hand side, and the cool thing is, on the right-hand side, we only have beta 1, beta 2, and beta 3, and also gamma 1 and gamma 2. But That's all. That's all the parameters we have. We don't have n parameters, n mu1s, right? Little n mu1s. So it's much simpler. We can also do the same thing for mu2, right? So by using both equations together, that's multiple equation reparameterization. We can now substitute this and this in for wherever we see mu1 and wherever we see mu2 in the big likelihood function. And then we can estimate all the parameters that we need. Okay, so that's fine. So that means we can estimate everything, no big deal. And I've told you that when we did this, there was this assumption, in addition to the assumptions of the model, of course. The assumption that I'm talking about is the variable that was left out of each equation. Those are variable exclusion assumptions. Those variable exclusion assumptions, it turns out, everything depends upon. So let's, I'm just stating that, but let's show that. What happens if there's no variable exclusions? Like what happens? So suppose we drop x2 and x3 from the systematic components. Remember, x2 is only in one equation, x3 is only in the other equation. What happens if we drop them? So we get this simplified expression from the previous page. Looks okay so far, right? Okay. But once we simplify, we get this. I don't know, we could substitute this in. What would we get? Well, it turns out the likelihood is not identified. Okay, well, that's interesting. What does that mean? How do you know it's not identified? Well, here's an example. So if beta 1 is 1 and gamma 1 is 30 and beta 3 is 555 and gamma 3 is minus 30, I did just pull that out of my hat, but you couldn't do that just sitting here. You have to just substitute some numbers in here. But if you do that, it turns out that mu1 is equal to minus x1. Okay, now minus x. So where does that get us? Okay, well, it turns out that this same result is going to come from beta equal 1, gamma equal 1 instead of 30, beta 3 equal minus 999 instead of 555, and gamma 3 equal minus 1 instead of minus 30. And you get the same result. Okay, so and it turns out as long as beta 1 is 1 and gamma 1 is equal to minus gamma 3, then for any value, regardless of what beta 3 is, mu1 is equal to x. Okay, right? Mu1 is equal to x, no matter what. So that means that beta 3 is clearly not identified, right? Because for any value of beta 3, you're going to get the same answer. It doesn't matter. So the result here is if you make a mistake with respect to x2 and x3, you get the wrong answer. If, however, you're close, you'll get a different answer. If you are a little farther, you'll get a different answer. If you make a different zero effect assumption, of zero variable exclusion assumption, you'll get a different answer. What we're showing here is high levels of model dependence due to the variable restrictions. Okay, so what about other approaches? You may have heard of other approaches. And there are lots of choices. There's instrumental variables, there's two-stage least squares. I remember explaining to somebody, a senior member of the profession, what two-stage least squares was years ago, and he said to me, yeah, and I suppose there's a three-stage least squares too. Yeah, actually there is. There's a whole bunch of these methods that attempt to deal with endogeneity, that attempt to deal with y causing x. But they all depend upon assumptions equivalent to or very similar to the variable exclusion assumptions. They're crucial assumptions. You can't, if we say that parents' party ID is left out of the vote equation and has therefore no effect on the vote equation, we cannot estimate that. Because if you try to estimate it, then it's not identified, so there's nothing to be estimated. You can't estimate it. It's a dumb question, actually. It seems like a good question, but it's not. It's a dumb question. So you can't estimate it. You must assume it. If you assume it, your answer depends exquisitely sensitively on the assumption. That's true for all these methods. That doesn't make the methods wrong. It doesn't make them bad. It makes them model dependent. It makes it crucial when you're studying them, when you're evaluating somebody else's paper that uses them, and when you're deciding whether to tackle a problem of endogeneity yourself, you have to worry about these variable exclusion assumptions. If you have good evidence as to why a variable has a coefficient of 0, a variable that you could not include in an equation to test, a variable for which you have very little evidence of, but if you know from prior research or theory or something that the effect is 0, fine. But if you don't know that the effect is 0, then you're going to get very model-dependent results, okay? So should we believe them? Now, this is a really important point because I want you to be skeptical when you come up with problems of endogeneity. I mean, people will, like routinely, somebody comes into my office and says, okay, somebody told me I have the endogeneity problem. Where's the button in SPSS I can push to fix that problem? It's not like that, okay? It's a very, very difficult problem. And to get a feel for it, my example is my daughter Ella, who when she was very little, I put her up on a chair right in front of the mirror. And I said, look in the mirror. Do you see that girl in the mirror? She said, yeah. You see the girl in the mirror? She's making you do things. And Ella said, no, she's not. And I said, yes, she is. Look, she's making you do things. Every time she picks up her arm, you pick up your arm. She said, no, I pick up my arm and then the girl picks up her arm. No. Also, look, if you bend over, you're bending over because she bends over first. She said, no, I bend over. I said, Ella, how do you know? How do you know that you are causing her to move rather than her causing you to move, right? Actually, let's pause here. Can you design an experiment to prove that it's one versus another? No, but really, so she said, okay, well, I will think of something that I'm going to do, and then I will do it. And then that causes the girl to move. And I said, no, the girl in the mirror, she thinks of it first. That causes you to think of it, and then you do it, right? After she does it, of course, right? And basically, it's a very hard problem to solve. My daughter is now a PhD candidate in physics, and I told her I was going to tell the story again, and I said, what would you do now? And she said, oh, I would do this experiment in a medium in which light goes so slowly you can watch it. Yeah, all right, well, anyway, good answer. All right, so that's a very hard problem. Design the experiment to solve that problem, right? What do? What you need is something external. Right? That was sort of Ella's solution. Like, I would think of something, and I destroyed that belief in her, right? But what you could do is she could be there, and maybe we could be external to that system, and we could, poke her, and not poke the person in the mirror and see whether the mirror responds. Of course, the story is really horrible, because then somebody could say that the person in the mirror caused the person next to him. In any event, you absolutely have to have something external to the system. Something exogenous is the phrase, totally exogenous. There has to be a zero exclusion assumption. It has to be the case that external influence on Ella has no effect on the girl in the mirror. Right? Now, I don't know how you set that up to convince ourselves, but it's the same thing. It's the same zero effect assumption. It's the same variable exclusion assumption. Okay. So my advice about endogeneity is, wherever possible, choose a different project. Wherever possible, it's not always possible, but wherever possible, avoid problems with endogeneity, particularly in observational research. I mean, if you have an endogenous dependent variable in an observational research, one option is change the question, right? There may be something else that you could go after that would be really interesting and compelling and of interest to your audience that doesn't have an endogeneity problem, because no matter what you do with that one observational data set, you're going to get questions about it. If you worked on it for 5 years, you would be able to improve your evidence about it step by step by step, but you're never going to get to a place where you would be if you chose a question without endogeneity. It's just a very hard problem. Okay, so you might ask me, what would you really do? I would go collect more data. Okay, I would go run an experiment, run a randomized experiment where I get to be the variable exclusion assumption. I get to intervene and randomly assign the treatment to one group and not the other group. And as long as I'm doing it, or I'm causing it to be done as a result of randomization, my randomization intervention, then I know that it can't be it can't be a result of the outcome variable. Exogeneity is not the same as randomness. Okay, randomness gives us exogeneity, but exogeneity is not necessarily randomness. And so, think about an earthquake. So there's an earthquake, or a pandemic, or something else that was utterly unpredicted. That's plausibly exogenous, but it's not random, right? It might have happened, and moreover, it's only an observation. It's only an observation it only has one observation, right? If you want the benefits of randomness, you need investigator control over treatment. That gives you exogeneity. You would like random treatment assignment. That gives you that gives you uncorrelatedness between the treatment and all other variables, including the outcome variable, so there's no endogeneity. And then with those two things, what else do you need? Well, randomization, of course, is you're doing things randomly. If you only had two observations and randomly assign them, it's not going to get you very much. You also need a large N. So if you had a large N, random assignment controlled by the investigator, then you could get around the endogeneity problem. So if you ask me what I would do, I would change the question and collect some more data. Change the question or collect some more data. Either one would be a really terrific advantage. So the last topic here for today is multinomial choice models. With k greater than 1, nominal choices from which one is chosen. So we did logit and probit, and those are dichotomous. We did ordinal probit, as I mentioned earlier. We're now going to do multinomial choice models. So an example is choice among candidates by voters, dishes at a restaurant by customers, war, peace, limited war by countries. There's lots of examples in which there's discrete outcomes. There's no necessary ordering among the outcomes, and we choose among them. These are direct generalizations of binary logit and binary probit. Turns out they generalize in somewhat different ways with pretty big consequences for computation and interpretation. All right, so let's start with multinomial probit, which is more difficult, but has certain advantages, and then we'll do multinomial logit. So remember the utility interpretation of multinomial of binary logit. We'll use that here. So now we're going to have U of I being multivariate normal with mean mu and variance sigma squared, but there being a whole bunch of these. And then there's a set of equations, one for each one of them. There's got to be an observation mechanism. The key difference here is the observation mechanism. So y sub ij is going to be 0 or 1, and the 1 is what choice is it? Which of the nominal choices is it? And the key thing is from an economics perspective, is you're going to choose the outcome that gives you the highest utility. So if there's 5 candidates, you're going to choose the candidate that gives you the highest utility, which means that candidate 3, if that's your choice, the U3 is larger than U2, U1, U4, and U5. And so that's what this notation does. It just says the observation mechanism is that although we don't see the utilities, we do see the choice of a candidate, and we make the assumption that people choose candidates that maximize their utility. So what's the stochastic component? So stochastic component is a direct generalization of the Bernoulli. It's the multinomial distribution. It's the probability of pi of I for observation, j for choice, equaling 1 is pi ji, such that the pi's over the choices fit in a simplex. That is, they're each probabilities, so they range from 0 to 1, and together they sum to 1. The systematic component works as follows. We'll take the differences between utilities, so then the observation mechanism can be written this way, and then pi of ij is the probability of choosing one of those, is the following. So then y star has to be greater than 0 and all the rest less than 0, which basically means that your utility is for that particular candidate is larger than any of the others. So I'm switching from the economic interpretation to the biological interpretation. Now, here's the hard part. Easy conceptually, just hard computationally. To get from one of the U's being higher than all the others, we take that down to the biology interpretation and have one of the Y stars being the one that's greater than 0. How do we get that? Well, this probability is calculated from the stochastic component, not here, but where this is derived from, which is the distribution of the utilities, which is multivariate normal. And since it's multivariate normal, we basically have to take a piece of the normal that reflects when the utility for candidate 3 is higher than the other utilities. And that's what this integral says, okay? You know, if you collapse over the other dimensions and you make sure that this one's greater than that one. It's a big multivariate integral. And as you may know, big integrals are hard to do analytically sometimes, and they're hard to do computationally sometimes. But this gives us the multinomial probit model. So here's the computational issues. There's no analytical solution for this integral. Doing it numerically for more than 4 or 5 choices you can't do. It would take forever. The problem has been solved when you do it by simulation. Just by simulation, it turns out you can do 9 to 12 choices depending on who you talk to, but it takes a long time. The problem is that even if you do that, all the elements of sigma are not identified, so you have to work hard on figuring out which elements of sigma are identified. The entire model is only weakly identified, by which I mean, what does that mean? Because I haven't defined that. It means that there's a lot of model dependence. You can be close to non-identification. The likelihood surface is relatively flat, but even if there's a unique maximum. The model is a straightforward generalization of SURM with an observation mechanism. In fact, that's the only difference. This stuff used to basically just exist in the textbooks, and I was once reviewing a paper, and the paper had a multinomial choice problem. It described substantively the particular substantive reason I'm about to explain as to why and when you should choose multinomial probit. And I was the reviewer, and I said, hey, you know, you should just switch to multinomial probit. And the editor wrote me a couple months later and said, the author tried and didn't know how to do it and couldn't really figure it out. Can you just like break the veil of anonymity and help him? And I said, sure, of course. And I called him up and we talked, and it turned out that he was doing all the right things, but following the textbook advice with the standard software program didn't work because some of the elements of sigma were not identified, and so we had to come up with restrictions on sigma so we could estimate it. So be careful what you say is easy. What I explained to the editor was, this is easy to do. Textbooks all describe it. Just have them go do this. In any event, that's multinomial probit. Multinomial logit is a lot easier to run, but has some other assumptions. So let's talk about that. The binary logit model, we know from before, probability of y is 1 is pi, probability of y is 0 is 1 minus pi. We can rewrite the logistic functional form. This is the form you've seen, 1 over 1 plus e to the minus x beta. This is also equal to this form. You just it's just a little bit of algebra gets to the second one. The multinomial logit model uses the second expression. So probability of pi ij equaling 1 is pi ij, such that it falls on a simplex. And then pi ij is equal to e to the xj beta divided by the sum of all the other e to the x k beta k's, right? So the sum of all of them, this is the one for your choice. So the math is a little bit different. It is, however, identical to binary logit when j is equal to 2, right? Because it's exactly the same thing. So it's a direct generalization. The likelihood is a very simple direct generalization of binary logit. Okay. There's a key assumption that makes multinomial logit appropriate. If it's not right, then multinomial probit could be appropriate. But of course, it makes other assumptions like normality and stuff like that, so it may be wrong. But let's understand this assumption because it's very substantive and meaningful. It's the independence of irrelevant alternatives. Turns out there's an assumption by the same name in social choice that means something else. Okay, under multinomial logit, the following is true. So pi 1, which is the probability of outcome 1, probability of outcome 2, is equal to this divided by this. Those are just the two systematic components. Remember, the denominators are the same. So it simplifies to this. No big deal. But the big deal is that the ratio of the probabilities of choosing option 1 and option 2 are not a function of choices 3, 4, and 5, or however many there are. That's pretty important. So it's independent of other alternatives. Under multinomial probit, the probability ratios are always a function of all the alternatives. Okay? Maybe not the right ratio, but they're still a function. In multinomial logit, they're not a function at all. Okay, so this is famously known as the red bus, blue bus problem. So the way this thing works is, people studied transportation, and the question is, do you want to go to work by car or by a blue bus? Okay, so let's say it's 50-50. Okay, and then they say, well, wait a second. Now you can have another choice. It could be a car, a blue bus, or a red bus. Now, if you don't really have color preferences, then what you do is you split that second probability, 0.5, into two probabilities of 0.25 and 0.25 for the red and the blue bus. Then the ratio of the car to the blue bus is 1-to-1. The ratio, right? It's 1-to-1 to begin with, right? But when you add the extra alternative, it's only 1 to 0.5, right? So it's 0.5 to 0.5, and then it's 0.5 to 0.25 just by adding a seemingly irrelevant alternative. So that, unless you take that into account with the explanatory variables, multinomial logit makes the assumption of independence of irrelevant alternatives, and the red bus, blue bus problem would violate that assumption. Candidates, of course, this is almost the definition of what presidential primaries and other primaries are about, because you may have, let's say, 30% of support among the electorate as a candidate, and that's a fine thing, but you're not going to win the election. But if there's 5 candidates who have, if you're a conservative and there's 5 liberal candidates and they split the remaining 70% of the vote, then you're going to win, right? So then there's a dependence of irrelevant alternatives. If there is dependence, then you can't use multinomial logit unless you control for it appropriately with the right explanatory variables. Okay. There's a question as to whether it matters empirically, and there's a question as to whether this matters empirically more than the estimation uncertainty. Because in general, it's okay to have a methodological problem and not correct for it if correcting for it is smaller than your standard errors, right? Because why would it matter, right? So you have to figure out whether it matters here and whether it's worth it going to the more complicated multinomial probit model or some other model that allows for the dependence of irrelevant alternatives. Okay. Let me give you a replication. This is a replication of Dominguez and McCann, which appeared in King, Thompson, Wittenberg, the clarified paper I mentioned earlier. All I'll say about the authors of the original paper is Jay McCann is a really terrific guy. Don't hold anything against them. Salinas, here's the application. Salinas, of the ruling PRI party, won the 1988 Mexican presidential election. Okay, so in 1988. And if voters had thought the PRI was weakening, who would have won? That was the question. That's a really interesting question, because they had won this long string of elections for like 70 years. So maybe they would have flipped, right? And so how do you study this question? Well, they ran a survey, and the model was a multinomial logit model with 3 choices. There were 3 parties. One choice was vote for Salinas from from the PRI, one for Clothier, which was from the PAN, a right-wing party, and the other is from there's a third one, which is the head of the leftist coalition. And then there's 31 control variables, which presumably were pre-treatment, the causal effects. But in this case, we're interested in the counterfactual. So here's the model. Y is multinomial. There's three outcomes. Vote for the PRI and the PAN and the leftist coalition. There's a multinomial logistic functional forum. There's three candidates. And then this is what the results look like, okay, when we reran the model and found an alternative way of looking at things, okay. So this is, again, a ternary diagram, which I've shown you before. This is where Salinas gets 100% of the vote, Cardenas gets 100% of the vote, Clothier gets 100% of the vote. And these are win regions that we drew on here. If you're in this region, this candidate wins a plurality of the vote. Each point is a simulation from an election outcome, a simulated election outcome, where all the voters believe, according to our flipping the explanatory variables, that the PRI is strengthening. So it's a counterfactual because everybody didn't believe that. But if we flipped everybody to believing it, then they wound up here. If the PRI, the ruling party, was strengthening, then they all voted here. If they thought that the PRI was weakening, then it was pretty much a toss-up, okay? Which is really interesting. That's what we analyzed. That was our conclusion from analyzing these data. If the voters believe the PRI is strengthening, the PRI wins easily. If the voters believe the PRI is weakening, it's a toss-up. And the interesting thing is, despite voter fraud, Salinas probably did, according to our analysis anyway, defeat a divided opposition in 1988. Eventually, that is in the next election, the PRI eventually actually lost for the first time after 72 years in power. So Mexico became a bit more democratic. And maybe it was presaged in that early stage, in that early analysis in the previous election. In the previous election and in the analysis of the previous election. So that's multiple equation models. It is not remotely everything you need to know about multiple equation models, but it's key factors that will enable us to go on. So the next topic that we're going to tackle is missing data. We will use these multiple equation models in order to build models of imputation for missing data, basically filling in the missing data and analyzing it in appropriate ways so your standard errors are right, no bias is introduced, and you can deal with the Swiss cheese data sets with big holes in it for the missing data in appropriate ways. So I look forward to seeing you then, and thanks for listening. See you next time.